Hi, welcome. In this video segment, I want to talk about something that is often kind of glossed over a little bit in chemistry classes, but it's an application of Le Chatelier's principle, for example, that I think is fairly important. So this is a table of temperature and Kw. Remember, Kw is the dissociation constant for water. So I'd have H3O plus times OH minus. And it comes from the fact that water, to a very small extent, will react with itself, and one water acts as an acid, one as a base, and we would end up getting hydroxide ion and H3O plus. Now, if we have pure water, these two must be equal to one another. So in pure water, with no contaminants, OH minus is equal to my H3O plus. Sorry about that. Let me rewrite that. My H3O plus is equal to my OH minus. Okay? So we can do a series of calculations here. I want you to note first, though, I realize the scientific notation is not correct here. This is not that uncommon. What is done is they set the table up so the power is the same. So what we can see here very clearly is that as you increase temperature, you increase Kw. Okay, so the table shows that very clearly when those powers are that way. So let's delve into this in a little bit more detail. Let's first look at 0 degrees Celsius. So we would have H3O plus times OH minus. This time it's equal to 0.114 times 10 to the minus 14th. Now, since these are equal, we can say we have x squared is 0.114 times 10 to the minus 14th. So x, which is our H3O plus and our OH minus, they're equal, is the square root of 0.114 times 10 to the minus 14th. And what we would get then is our H3O plus is equal to 3.38 times 10 to the minus 8th molar. Not totally worried about sig figs yet because I'm just making a conceptual point. So if I take the negative log of that, I get pH equals 7.47. So this is a neutral solution. My OH minus is equal to my H3O plus. That means it's a neutral solution, and yet pH isn't 7. Blow your mind. You've been told that your whole life, haven't you? So now most of you have young lives, but you've still seen that and talked about that. So it is pH is temperature dependent, and that's kind of the point I want to make here. And so let me do one more quick calculation, and let's do 100 degrees. So if we did 100 degrees, we'd have x squared, following the same algebra as above, equal to 51.3 times 10 to the minus 14th. So x is equal to the square root of 51.3 times 10 to the minus 14th, which is equal to 7.16 times 10 to the minus 7th molar for my H3O plus and my OH minus and my H3O plus. So pH is equal to 6.14. Okay, so you notice that as you increase temperature, we increase Kw and we decrease pH of a neutral solution. Right, now let's apply that to Le Chatelier's principle. So my question is this reaction, is this self-dissociation of water, self-ionization of water, exothermic or endothermic? So let's process that. Remember, we have two waters yielding, whoops, I did not mean to make that bracket. Sorry about that. H3O plus OH minus. So you notice that as we increase temperature, Kw increases. Now, it's very common for students to think molarity changes Kw. Molarity does not change Kw. Changes in molarity will shift the position of an equilibrium, but the value of Kw would remain constant. In this case, the temperature changes, Kw changes. Well, if Kw have increased, that means we had increased products. So an increase in temperature caused the reaction to shift to make more products. So if you look at this, we've added heat. If it's endothermic, heat is on the reactant side. If it's exothermic, heat is on the product side. Okay, an increase in temperature, I have a little pencil trick I use, but if we increase temperature means we added heat and that shifted to the right, that must mean that our reaction was not exo. If it had been exo, added heat would have shifted to make more reactant. It's not exo. That means we have an endothermic reaction. Increases in temperature always favor the endothermic direction. So in this case, it would be endothermic in the forward direction rather than exothermic in the forward direction. So, wow, kind of a little tough topic there, a little ambiguous maybe, a little abstract, but hopefully I was able to help you with tie together a few little concepts there. Thanks for joining me.